So yes, so in case of optical coupler, क्या है ऑप्टिकल कपलर और क्यों इसकी जरूरत पड़ती है, इसको जरा हम देखें। तो मान लीजिए एक पीस ये है फाइबर का, दिस इज फाइबर का एक पीस है F1, और दूसरा पीस ये फाइबर का है F2, मतलब दो टुकड़ा है। अब इसको हमें यूज करना है, तो यूज करने के लिए एप्लीकेशन है, दो पीस का एप्लीकेशन करना है। तो एप्लीकेशन के लिए सबसे पहले क्या चाहिए, सोर्स। सोर्स मीन्स ऑप्टिकल सिग्नल, यहाँ पे सोर्स क्या होगा, ऑप्टिकल सिग्नल। और दूसरा होगा फाइबर इटसेल्फ, है ना, और तीसरा होगा डिटेक्टर। तीसरा होगा डिटेक्टर, कि जो भी सिग्नल गया वो कहीं ना कहीं डिटेक्ट हो कि क्या सिग्नल आ रहा है। जैसे आप डिटेक्टर हैं, हम यहां से भेज रहे हैं सिग्नल और आप डिटेक्ट कर रहे हैं अपने एंड पर, और आप जब भेजते हैं सिग्नल तो मैं डिटेक्ट करता हूं। तो ये जो 3 पॉइंट है, सोर्स, तो सोर्स क्या होगा, सोर्स टू फाइबर कनेक्ट होगा पहले, है ना, सोर्स से फाइबर कनेक्ट होगा। मतलब मान लीजिए ये एक सोर्स है, दिस इज सोर्स, तो ये सोर्स से ये फाइबर की एक कनेक्टिविटी बनेगी, सोर्स टू फाइबर, ताकि यहां से जो सिग्नल है वो फाइबर में आ सके। ठीक है, अब फाइबर टू फाइबर का मतलब क्या होगा, F1 से F2, मतलब लिंक बढ़ाना है। लिंक बढ़ाने का मतलब कि ये F1 है और ये F2 है, तो इसको सिग्नल यहाँ आ गया, वो सिग्नल फिर दूसरे फाइबर में जाए, तो फाइबर से सिग्नल कहाँ गया, दूसरे फाइबर में। अब यहां पर द एंड ऑफ द सेकेंड फाइबर, ये क्या है, डिटेक्टर। डिटेक्टर मतलब कितना सिग्नल आया, इसको आपको चेक करना है, इसको आपको चेक करना है। तो इस तरह से आप देखिए कि एप्लीकेशन को ध्यान में रखते हुए सोर्स माने ऑप्टिकल सिग्नल से लेके फाइबर में तो एक कनेक्टर हुआ, दिस इज द कनेक्टर। दूसरा फाइबर से फाइबर में आप जोड़िए तो यहां भी कनेक्टर हुआ। और डिटेक्टर का मतलब हुआ फाइबर से डिटेक्टर, फाइबर से डिटेक्टर। तो फाइबर से डिटेक्टर में भी क्या यूज होगा, कनेक्टर, स्प्लाइसेस एंड कपलर, देयर आर 3 वर्ड्स वी यूज। तो यहां पर दिस पार्ट इज मान लीजिए ये कह दें कि हमारा C1 है कनेक्टर, दिस इज C2 कनेक्टर, और दिस इज C3 कनेक्टर। तो वी कैन कॉल दिस वन इज as this one is C1, एक कलेक्टर ये हो गया, यहाँ पर C2 हो गया फाइबर टू फाइबर, और ये हो गया C3 फाइबर टू D। दिस इज फाइबर टू डिटेक्टर, ठीक है, फाइबर टू डिटेक्टर, ये आपका पॉइंट हो गया। तो देयर आर थ्री बेसिकली points where we want to connect the source to fiber, fiber to fiber, and fiber to detector in order to detect the things. तो इसको करने के लिए, इसके पूरा डिटेल करने में हम 2 पॉइंट को बहुत ध्यान से देखते हैं। एक पॉइंट तो ये होता है कि जो इंटरकनेक्टर्स हैं इसका नेचर क्या है। सो the interconnection occurs at the 3 specific points, marked as C1 source to fiber, C2 fiber to fiber, and C3 fiber to detector. Fiber to detector. The particular technique selected for the joining the two entities depends on the nature of bonds. Nature of bonds का मतलब first permanent bond, or the second is not permanent, it is known as demountable bond. Permanent bond and demountable bond. Permanent bonds are generally connected with splices. There is need of splices, and demountable bonds are joined by the connectors. There are two specific words that are used in case of the joint, what kind of the system we are using. So every joining technique is subject to certain conditions. Which can be amounts of optical power loss at the joint. These losses depend upon the distribution of the power. How it is distributed, these things are there. So and it depends upon various factors, as first है the input distribution. Input distribution means from source to fiber. Input distribution. दूसरा है the length of the fiber. The length of the fiber means the first one is, suppose this is source and source to fiber. This is fiber. So from this point and this one fiber to another fiber, this is F1, F2, something like this. And third point is the geometrical and waveguide. Geometrical and waveguide characteristics. Waveguide characteristic of the fibers. So these are the three important parameters on which the optical loss depends. The optical power that can be coupled from one fiber to another is limited by the number of modes. Number of modes that can be propagated in each fiber. And is for the total number of mode modes in a graded index fiber. Graded index fiber, that is GIF, can be expressed as M is K square 0 to A mu of R minus mu square R into dr. R into dr, where mu R defines the variation in the refractive index profile. Refractive index profile of the core. Because we know that the graded index fiber has the variation in the refractive index, and then that depends upon this can be related to a general local numerical aperture NA. So this Total number is, this is k square 0 to a numerical aperture square into dr. This can be expressed as k square n a0 square 0 to a. This is 1 minus r by a to the power alpha r into dr, where alpha is index of profile, index of profiles. Thus the fraction of energy, thus the fraction of energy coupled from one fiber to another is proportional to the common mode volume, that is m c common. The fiber to fiber coupling, the fiber to fiber coupling, and F is given by eta F is m common volume divided by me, number of modes in the emitting fiber, where me is the number of modes in the emitting fiber, the fiber which lends the power to the next. And fiber to fiber couple loss is also, this is also expressed as minus 10 log, this is 10 log, this is enough, that is minus 10 log m common upon me, m common upon ne. So this depends upon the geometrical part. So in case, let the case 1, what is the case 1? When the modes are excited equally. When modes are excited equally. Modes are excited equally means, so what kind of the modes? TEM mode, yeah, T1M, something like this. So if this is the core and here it is cladding, this part is core, this part is core, and here it is This is fiber. This part is core. And from this core, these are the all modes are equally excited. Full numerical aperture of the fiber. This is full numerical aperture of fiber. This is full numerical aperture of the fiber, or simply this can also be drawn as this is the core, and this core is equally fielded with this fiber. For the receiving fiber to accept all the optical power emitted by the first fiber. There must be perfect mechanical alignment. Perfect mechanical alignment. And geometrical wavelength characteristic mismatched and geometrical and waveguide characteristic must match precisely first. And the second case, that is propagation mode in the steady state. Means suppose this is the core and here it is cladding. So in this fiber, this part is propagating. This part is propagating, that is used for the propagation. This is cladding. So we can draw, this is the core. This is core part, here it is cladding. But only this part is used. This is partial. This is the partial field fiber. This is partial field fiber. And in place of this, there are three mechanical misalignments misalignments that can be occurs between two joint. For example, this is the one fiber. These are the cladding part, and here it is the core part. This, so these are the change. This is your D. This is your D. So it is called lateral. This is called lateral. And in this lateral, the loss can be the the lateral offset D by A, the lateral offset D by A there is excess loss there is excess loss. So this excess loss is something like this part. Here it is theoretical, and this is experimental. Experimental loss in dB. So this is lateral. Now we can have longitudinal. That is, suppose this is the fiber and the other fiber are at certain distance. Other fiber are at a certain distance. This is your cladding. This part is cladding, and this is longitudinal, that is end separation. That is end separation. That is longitudinal end separation. So we can plot this as, that is axial separation is by A, and this is the loss. This loss is again in dB, and this is experimental, and here it is theoretical. And the third is angular. That is this is theta, angular theta. Angular joint, and the angular is sin theta upon NA, and this is This is the experimental, and here it is. This is theoretical. This is your theoretical, and this is your DB. So on the basis of alignment, there are various kind of the losses, and these losses persist in the fiber. Now connectors. Connectors are available in various configuration which are given as first butt joint. Butt joint is also called as straight sleeve. Straight sleeve. So this is something like sleeve. This is something like sleeve, and in this sleeve, this is the way to pass the fiber. So this is termed as guiding ring. This is alignment sleeve. Alignment sleeve. And second one is tapered. Tapered sleeve. Tapered sleeve are biconical. Biconical. So this can be so this one is, as we have fiber. This one is the fiber, and this one is guiding ring. And this part is sleeve. This part is alignment sleeve. And the third one is expanded beam. The expanded beam is very popular. Suppose this is a lens, here it is another lens, and now this one is the fiber. From this fiber there is focusing of this part, and now this one is parallel communication. And this parallel communication is something like this. So transmitting fiber, here it is the transmitting fiber, and this is receiving fiber. This is your receiving fiber. So a wide variety of optical fiber connectors has evolved for numerous different applications. Different applications. Some of the requirements of a good connected design are as follows. First, low coupling loss. Use such type of coupling that is loss is minimum. Interchangeability. Third, ease of assembling. Fourth, low environmental sensitivity. Fifth, low cost and reliable constructions. And six is ease of connections. So these are the requirements for the various type of the connectors that are used. And now the splices, fiber splices, the technique which is used for joining the fiber permanently is generally referred to as a splice. Many different fiber splicing techniques have arisen during the evolution of optical fiber technology. These are as first fusion splices, second is V groove, third is tube, mechanical, fourth is the elastic tube, and fifth one is rotary splices. These are shown as first fusion, in fusion what are going, suppose this is a fiber, this is fiber 1, here it is another fiber, so we put these two on the electric arc. This is electric arc or laser fusion. And then what happens? These are the spark coming out. And these are the connected. And here are holders. These are the holders which hold the fibers. So fibers are grouped under a microscope with micro manipulators. Why? Because radius is of the order of micron, 10 to the power minus 6 meter, and that's why it is whole mechanism is done with the help of the microscope. The butt joint is then heated. Butt joint is heated with the electric arc or laser fusion techniques. The second one is V group. The V group. V group is the technique, something like this fiber is put in the group, splices, and so fiber to be spliced and fiber ends exposed, clamped here, ends are clamped here, and this is V grouped. V grouped subthread. And third one is elastic tube. These are the elastic materials. These are the elastic materials, and here it is the fiber. This is the fiber and tapered opening. Axial alignment. This is the axial alignment, and therefore the fiber that is here, these fibers are connected. So these are the three important techniques through which we can connect the fibers, and due to the heating, oblique V grouped, oblique elastic intact, elastic intacts, the surface defect growth created during the alignment and stress induced stress induced near the joint. As a result of changes in the materials which weaken the fiber. Therefore, there should be minimum use of the splices in the network. मतलब जो भी हम यूज करते हैं कनेक्टर्स के रूप में, उनकी जो संख्या है वो संख्या बहुत ज्यादा नहीं होना चाहिए, है ना। और इस तरह से these are the important concept of the connectors and splices.